Hi, welcome back to the thermodynamics and heat transfer class. Last week, we already learned about the some mechanism of the heat transfer such as conduction, convection, and radiation. However, start from today, we will focus on each mechanism of the heat transfer. Start with the conduction. Today's topic will consist of the conduction rate equation and the thermal properties of matter. Specifically, today we will learn about the thermal conduction, Fourier's law, heat flux, and thermal conductivity. Let's begin with our first main topic, thermal conduction. The thermal conduction or heat conduction occurs within a body or between two bodies in contact without the involvement of mass flow and mixing. So remember, there's a mass flowing and mixing, so there's no convection here. It is direct microscopic exchange of kinetic energy of particles through the boundary between two systems. Heat transfer by conduction is dependent upon the driving force of temperature difference and the thermal conductivity, or sometimes we call it the resistance to heat transfer. The thermal conductivity is dependent upon the nature and dimension of the heat transfer medium. All heat transfer problems involve the temperature difference, the geometry, and the physical properties of the object being studied. In conduction, heat transfer problems, the object being studied is usually solid, but not limited to solid. Microscopically, this mode of energy transfer is attributed to the free electron flow from higher to lower energy levels, lattice vibration, and molecular collision. So this is the example what is called the lattice. The lattice on the solid material. So we can see there is an atom, and atom. Means in Indonesian is called a kiss of the atoms or something like this. And the molecular collisions means the molecule inside a solid phase or inside the phase of matter is collide with each other. So this is the example of the lattice vibration. So the lattice can be assumption as a spring. So the molecule can be vibrate. And this is the example of the molecular collision. So between each other, since there is a vibration, if the molecule is near to each other, they might collide with the neighbor atom or neighbor molecule. So now we consider a block of stone. Okay, block of stone, something like this. This is a stone. So the stone is at high temperature, and stone, of course, consists of atoms that are oscillating intensely around their average positions. At low temperatures, the atom continues to oscillate but with less intensity. If a hotter block of stone is put in contact with a cooler block, the intensely oscillating atom at the edge of the hotter block gives off its kinetic energy to the less oscillating atoms at the edge of the cool block. In this case, the energy transfer between these two blocks and heat flows from the hotter to the cooler block by the random vibration. So the modern view to ascribe the energy transfer to lattice wave induced by atomic motion. In an electrical insulator, the energy transfer is exclusively via this lattice wave. In conductor, it also due to the translational motion of the free electron. So this is the mechanism. So the heat is flow from the high temperature to the low temperature region. In general, metals are usually good conductors of thermal energy, and it's closely associated with its good electrical conductivity. For metals, the thermal conductivity is quite high, and those metals which are the best electrical conductors are also the best thermal conductors. So why? This is due to the way that metal bonds chemically. Metallic bonds have free moving electrons or free electrons that transfer thermal energy rapidly through the metal. The electron fluid of a conductive metallic solid conducts most of the heat flux through the solid. Next, we will learn about the conduction rate equation. So we consider the steady state conduction experiment like in this figure. So this figure, we can see this is a cylindrical rod. For example, it's a known material and it's insulated on its lateral surface. Okay, there is an insulator here. So this is insulated on its lateral surface, while its end faces, so this is the end faces, are maintained at different temperature, with the T1, this is the T1, is higher than the T2. Okay, I will repeat. So this is the cylindrical rod of known material, and on the lateral surface there is an insulator here, but both two faces are not covered by the insulator, and this T1 is higher than the T2. So the temperature difference causes conduction heat transfer in the positive x direction. So this is the Qx, means the heat transfer rate. So we are able to measure the heat transfer rate, or Qx, and we seek to determine how the Qx depends on the following variable. So the Qx, we want to know, it depends on the first variable is the delta T, or the temperature differences, the delta X, or the rod length, and the A, the cross-sectional area. In this case, in case of the cylindrical rod, the cross-sectional area is a circle. So we might imagine first holding the delta t and delta x at constant. So the delta t and delta x constant. So we will varying the A or the area. So we will find that the Qx or heat transfer rate is directly proportional to A. So if delta T and delta X are constant, so if we vary the A, so the Qx will directly proportional to A. And similarly, so we holding delta T and A are constant. So we will observe that the Qx varies inversely, so inversely with the delta X. So finally, if we holding the A and delta X at constant, so we find that the Qx is directly proportional to the delta T. So we can write something called a Fourier's law. So the Qx is proportional with the A if we hold the delta T and delta X at constant, and the Qx is proportional with delta T if we hold the A and delta X at constant, but the Qx is inversely proportional with the delta X if A and delta T constant. So in changing material, this proportionality remain valid. However, we would also find that for equal values of A, delta X, and delta T, the value of the Qx would be smaller for the plastic than for the metal. This suggests that the proportionality may be converted to an equality. Okay, so the proportionality, this is the symbol of the proportionality, may be converted to an equality. Okay, by introducing a coefficient K. So this coefficient K is the coefficient that is measure of the material behavior. Hence, we write this equation into this equation. So the proportionality converted to equality by introducing the K. So the K, so what is the K? The K is the thermal conductivity, and the unit is, remember, is watt per meter Kelvin. So this is an important property of the material. So when we evaluating this expression in the limit of delta X near to 0, we can obtain the heat rate. Remember, this is the thermal conductivity, watt per meter Kelvin, and we can find the heat rate or Q. If it's in x direction, it's called Qx, but heat rate, the unit is W or watt. So the equation of the previous equation can be written as follow. So minus K A is the area, dt dx, or the change of the temperature over the position in the horizontal position. Or for the heat flux, okay, now this is the new terminology. This is heat rate and this is heat flux. The unit is slightly different. So the unit of heat rate is watt. However, the unit of heat flux is watt per square meter. So the heat rate can be written as the Qx with the double prime. So it means per square meter, or the Qx or heat rate over A, or Qx divided by the area. So the equation with the A value on the right hand side will be vanished. So we have the minus K dt dx. So what's the meaning of the minus sign? The minus sign is necessary because heat is always transferred in the direction of decreasing temperature, or in other words, from the higher temperature to the lower temperature. Okay, the Fourier law is written here. This one implies that the heat flux is a directional quantity. Okay, directional quantity. So this is a factor. In particular, the direction of the heat flux is normal. Okay, remember what means normal. If you already learned about the applied physics or basic physics, you may found a force named a normal force. It means the force that perpendicular to the floor. Okay, so the keyword is perpendicular. So it means, if we have the something like this, for example, this is a surface, okay, surface of something. The normal means the direction is perpendicular. So sometimes we call this is the normal vector. Okay, so this is the example. More general, the direction of heat flow will always be normal to a surface of constant temperature. Okay, the surface of constant temperature, or we call the isothermal surface, and the heat flux is always in this direction. So this is perpendicular to this position. So it's called normal. And from this equation again, it follows that the heat flux is positive because the temperature gradient is negative. The dt over dx is negative. So since there is a minus sign here, so the heat flux will be positive. Okay, so we can see again, this is the example of the, I will erase this one. Okay, yeah, okay, so this is the example of the temperature distribution. Okay, this is the example of temperature distribution in one dimensional slab. Okay, so we can see that the dt over dx is negative. Okay, so heat flux is a vector quantity because it has a magnitude and it has a direction. It has a direction. Okay, then in general, so we can write the Fourier law in terms of this equation. Wow, what is this? Okay, please don't be amazed. So this one minus k, the k is heat transfer coefficient, and this upside down triangle is called the del operator or nabla. This is del operator. So it means this is the gradient. It means del t is called the gradient. Since we have the three-dimensional three-dimensional coordinates x, y, and z, sorry, x, y, and z, or in the unit vector is called I, j, and k. So this one, the gradient, it means the fractional or partial derivative of the temperature on the x direction. Okay, maybe you already learned this term in a mathematical class, I hope. So finally, if we separate into the vector in the each direction of the Cartesian coordinates, we will have the heat flux in the x direction is equal to minus k delta t. Sorry, this is round d. It's like a d, but it's more round. Sometimes called round d. Sometimes it's a round t. Sometimes it's called is dou t. So maybe in English is the correct term is round dt. Okay, round dx, and this is the same with the y and also with the z direction. Okay, now to make you more understand about this heat flux equation or Fourier's law equations, let's continue with the problem. Okay, this is the example of the problem number 1. So imagine we have a slab of lead. Okay, slab of lead. So the front of slab of lead with K, this is the thermal conductivity of the lead, is 35 watt per meter Kelvin. It's kept at 110 degree Celsius. And the back is kept at 50 degrees C. So we have two temperatures. The higher temperature is 110 and the lower temperature is 50 degrees C. So if the area of the slab is 0.4 square meter and it's 0.03 meter thick, it means 3 centimeter thickness. Compute the heat flux and heat transfer rate. Okay, remember heat flux, it means Q double prime, and heat transfer rate or heat rate is only the Q. So please imagine a slab of lead. Okay, this is in the case of the three-dimensional. Okay, three-dimensional slab. So for example, this is the area is 0.4, and this is the T back, the hottest part, and this is the front part on the coldest part. and the heat flux will go to this direction. Since this is a normal to the surface of isothermal surface, so we assume that this is the isothermal surface and already a steady state condition. So this problem we can simplify into one-dimensional slab. Okay, so we don't need to calculate into three-dimensional. So we can solve to one-dimensional problem. So we just see in this direction. Okay, so this is the thickness. This is a 0.03, and the the yellow line here means the temperature gradient. So what equation that we will use? So we will use the equation for the one-dimensional problem of the heat flux. So we have this equation. Please remember, we got this equation from the previous class, and I also show you in the previous slide. So it means the heat flux is equal K delta T over delta X. Please make a notice here. This one, there's no minus sign. Why? Remember that the delta T, okay, delta T, this one delta T, it means delta T, it means the lower temperature, okay, the low temperature minus the T of high temperature. Okay, so this value of low temperature minus high temperature will be a negative. So we can erase the negative part by change the delta is from the high minus low. So this delta here is not the low minus high, but the T high minus T low or T cold. Okay, please remember. Okay, so this is the figure of one-dimensional problem. So first we want to calculate the heat flux. So since we know that the K, what is the value of K? K is 35. Okay, K is 35. So by using this equation, we can get the heat flux is 70,000 watt per square meter. Okay, and in this case we have the T is of back is 110 and the front is 50. Okay, to calculate the delta T, you don't have to convert. Okay, you don't have to convert into Kelvin. Okay, you don't have, because even the delta T, you use the Celsius and the Kelvin, the result will be the same. Okay, this why it's easy for the delta to not to convert. But if we have the multiplication, you need to convert from the Celsius into a Kelvin. And next, okay, I need to erase because you won't see my. Okay, erase this one first. So the heat transfer rate or heat rate, of course, just multiplying the heat flux with the total surface area. So finally, this is this relation of the heat flux. So Qx, it means the heat rate is the heat flux multiplied by area. So we have 28 kilowatt. Okay, if you have a question, you can send a message into our WhatsApp group discussion. Okay. Okay, next is a more complicated problem. For the next one, we have a copper slab. Do you know what is copper? Copper is one of the metal that have a good heat conductivity or thermal conductivity, and it's cheaper than the gold or silver or platinum. So the heat, the K value is high. Remember, for the lead, the thermal conductivity of lead only 35. However, for the copper, it's 372 watt per meter Kelvin. So okay, focus again. So we have a copper slab, and the thickness is 3 millimeter. Okay, and it is protected from corrosion on each side by 2 millimeter thick layer of stainless steel. And the stainless steel has the lower thermal conductivity coefficient than the copper slab. So it's only 17 watt per meter Kelvin. If the temperature is 400 degrees C on one side of the composite wall and the other side of the wall is 100 degrees C, so we need to find the temperature distribution in the copper slab and the heat conducted through the wall. Okay, so we need to find the temperature division and the heat conducted through the wall. So from this problem, we can make an illustration. So this is still one-dimensional problem. So we will only have the x-axis direction here. Then we draw on the left hand side, we draw the stainless steel, okay, with the thickness of LSS. And next to the stainless steel, we have the copper with the thickness of LCU. And on the right side of the copper, we have another stainless steel, okay, the identical one with the previous, so the same thickness LSS. SS stands for the stainless steel, for the abbreviation. Okay, and next we know that the temperature is 400 degrees C. So assume, for example, this is on the left hand side, so this temperature is 400 degrees C. And since the copper is colder than the stainless steel on the left, so the temperature may decrease. Okay, so this is the temperature gradient, and the copper surface on the left side will have the temperature TLHS. It means the temperature left hand side of the copper, okay, is lower than the temperature of the surface of the stainless steel on the outer surface, but the inner surface of the stainless steel has the same with the copper. So we will have the delta T of the stainless steel. Okay, this is the delta T of the stainless steel. And we see again, so the copper on the right hand surface will have lower temperature than the left hand surface, with the temperature of TRHS copper. And this is the delta of the change of the temperature of the copper, because at the beginning is TLHS copper and at the end is TRHS copper. And we know also that on the right side surface of the stainless steel, the temperature is 100 degrees C, and the temperature gradient will be something like this, and this is the delta TSS, or delta T stainless steel. So from this illustration, and also if we see and we compare the thermal conductivity of these two materials, we see that the copper has the higher thermal conductivity than the stainless steel. So the value of the thermal conductivity of the stainless steel is like 1/20 of the copper. So it means also that the temperature gradient, if it has the higher thermal conductivity, it's not so large compared if the material has less thermal conductivity. And we can assume that the copper will virtually isothermal at the average temperature of, so this is 400 and this is 100, so it means around 400 plus 100 divided by 2, so the copper temperature may be around 250 degrees C. So we can estimate the heat flux by using this model. So we can roughly estimate the heat flux by neglecting the presence of the copper. But remember, this is roughly estimate. So remember, this is the equation of the heat flux. So this is the first, as we already seen on the previous slide. And if we neglect the presence of the copper, we only have the stainless steel with the thickness of 2LSS. Okay, so in this case we put the value of the K. Okay, this is, wait a moment, where is the, sorry, no, yeah, this one. Okay, let's use the pen. So the delta X for the roughly estimate will be the 2LSS, and the delta T will be 400 minus 100, and the K itself is only belong to stainless steel. Remember what is the K? Yes, the K of the stainless steel is 17. So we will have the roughly value of the estimation is 1275 kilowatt per square meter. However, the accuracy of this rough calculation can be improved by considering the presence of the copper. So, to do this, we first solve, okay, we need to solve the change of the temperature of the stainless steel, or the delta TSS. And we need to solve the change of the temperature of the copper or delta T copper. So we will use again this model, and by considering the conservation of energy, that the steady heat flux through all the three slabs must be the same. So the heat flux should be the same over the stainless steel and also through the copper. The value should be the same. So we will have this equation 1. Okay, this is the equation 1. This comes from the K delta T over delta X for the stainless steel and K over delta T over delta X for copper. So the heat flux, okay, will be the same. Even it's from the first stainless steel to the copper and the second stainless steel, the heat flux should be the same. Okay, same value. But in this case, we will have this kind of temperature. Okay, the change of the temperature, it means the delta TSS double, okay, plus the delta TCU, okay, this one. So this one plus this one plus this one is equal to 400 minus 100 degrees C. So we need to solve this one first. So this is become the equation number 2. Okay. So I rewrite again the equation number 1. So we need first is solve the equation number 1 to find the delta TSS or the delta T on the stainless steel. Sorry. Okay. How to solve it? First, we want to know the delta T stainless steel. It means this one is remain at the left hand side. So we have the delta T stainless steel will be equal to change the delta X here into the LCU and the delta X here into the LSS. So we have the equation will be brackets. Inside the bracket is K. So this K is belong to the copper. Over L also belong to copper. So we can write something like this. Okay, so it means K over L, okay, copper, and this one divide by the K here, and this K is belong to the stainless steel over the L of the stainless steel, multiply by the delta T of copper. Okay, so we can write something like this. So we have this relation, and if we want to have the two delta Ts, so we just multiply by 2. Okay, since the since the stainless steel is a 2, we have the double LS. Okay, next is from the equation 2. Okay, so we will have this equation, and we put the value of the 2 delta TSS equal to 2 multiplied by, remember, K over L of copper multiplied by, divide by K over L of the stainless steel multiplied by delta T of copper. So this one plus delta TCU by using the algebra, so we can have this equation. Okay, we can have this equation. You can try. It's simple. And the 400 minus 100, it means 300. So we need to find what is the delta TCU. Okay, if you well calculate it, you will have the delta TCU is equal to 9.94 Kelvin. Remember, this is the delta. Okay, delta. So this will be equal to 9.94 degree C. And then the next one, we need to find the delta TSS. So how to calculate? So we have this relation, okay, delta TSS. Okay, so we have this one is already equal to 300. Okay, and it should be minus the value of delta TCU. So it means minus of 9.94, and since we have 2, so it should be divided by 2. And finally, if you well calculate, we can say that the delta TSS will be equal to, sorry, please don't disappear. Okay, delta TSS will be equal to 145 Kelvin. Okay, remember, even it's Celsius or Kelvin, it doesn't matter because this is a delta. And then from delta TSS, we can know what is the value of the temperature of the copper of each side. Okay, next. Okay, so we can now this value, this one, and this one, because previously we already found that the delta T kappa, okay, so only this one is equal to 9.94, and we already know that the delta TSS, so the delta TSS here on the left and on the right has the same value, so delta S is equal 145. Therefore we can calculate, okay, by using the value of delta TS. So this value will be equal 400 minus 145, so it's equal to 255, and this value will be 100 plus 145, so this one will be equal to 245 degree C. So again, the heat flux can be obtained by applying a Fourier's laws to any of three layers. So we can apply it only to the, for example, you want to apply it to the stainless steel here, or we can also do to the copper. It's okay. This is also okay, no problem. So in this case I consider the stainless steel layer, but we just need to calculate one layer, no need to calculate two layers. So using again that equation, okay, using again this equation and put the K value of the stainless steel is 17, and the delta T, okay, which one? The delta T? The delta T in this case is 145, and the delta X, this value will be the LSS, or equal to 0.002 meter. Okay, remember, because 2 millimeter thickness. And finally, the heat flux will be equal to 1233. The unit is kilowatt per square meter. Previously we have the value of 175 by using the roughly calculation. So this is not bad, yeah, but there's an error with a few percent of error. Okay, do you have any question till now? I don't think so you have. Maybe you're still confused, but it's okay. You can consider and try to understand. If you have any question, again, please write on the WhatsApp group. If you cannot ask me in English, you can ask in Bahasa Indonesia, no problem. To make a better understanding. Okay, the next topic we'll cover about the thermal properties of matter. So it's only cover the thermal conductivity of fluids and the thermal conductivity of solid. So first, we will begin with the thermal conductivity of the meaning of the thermal conductivity. So the heat transfer characteristic of a solid material are measured by a property called the thermal conductivity, or K. And the thermal conductivity is most liquid and solids varies with the temperature. And again, what is the meaning of the thermal conductivity? The meaning of the thermal conductivity, it's something like to measure a substance ability to transfer heat through a material by conduction. Remember, by conduction. So there's no thermal conductivity of the convection or radiation. So the thermal conductivity is specific behavior of the conduction. If we have high thermal conductivity, it means heat can be transferred easily. So the heat loss is low. So for example, if we have like a slab here, okay, slab with the T hot and T cold, if the K is higher, it means the temperature gradient is not so slow, so only small gradient. It means it transfer the heat better. However, if inversely, if the thermal conductivity is low, it means the ability to transfer the heat is worse. So it depends on the necessary, which we need the higher thermal conductivity or low thermal conductivity. For example, we need an insulator, of course, because if we have insulator made by metal, of course, in the coldest part, it will be very hot, so it's not safe, and also it will be too out to the surrounding easily. So we need to insulate by using the insulator. It means on the surface of the insulator, the outer surface, the thermal conductivity, the temperature will be very low. So it's safe for the safety. And next, okay, from the very low in the x direction, so we can write again that this value is the heat flux equal minus K. Okay, the round dt over round dx. Okay, then we can rearrange this equation into this equation. Okay, so I will again erase this one. Okay, so you can see clearly. Yeah, this one is just arranging this previous equation into this equation. Okay, and then the both materials are very nearly homogeneous, so we can write the K is equal the K of the function of T. So it means it's not changed so much, so we can write only K. So the similar definition are associated with a thermal conductivity in the Y and Z direction. So the same. Kx, Ky, and Kz. And also for the isotopic material, the thermal conductivity is independent. Okay, independent. It means if change or something is not affect, is independent of direction of the transfer. So it's not, the direction of the transfer is not affect the transfer of the material, transfer of heat, only for the isotopic material. So it means the Kx, Ky, and Kz all is equal to K. And here, from the foregoing equation, it follows that the conduction heat flux increases with increasing thermal conductivity. Okay, the conduction heat flux is increased with the increasing of the thermal conductivity and increase with the increase of temperature difference. So if this one high, so the heat flux will be high. If the temperature difference is also high, it means the heat flux also high. And in general, the thermal conductivity of solid is larger than that of a liquid, which is larger than that of a gas. So the next topic is the thermal conductivity of fluids. Do you know what is a fluid? In physics, if we say a fluid, the fluid is a substance that continually deforms or flows under an applied shear stress. Fluids are subset of the phase of matter and include liquid, gases, plasmas, and some extent plastic solid. Because the intermolecular spacing is much larger and the motion of the molecule is more random for the fluid state than for the solid state, therefore the thermal energy transfer is less effective. And then the thermal conductivity of gases and liquids generally smaller than of solid. In case of the thermal conductivity of gases, the effect of temperature, pressure, and chemical species on the thermal conductivity of gas may be explained in terms of the kinetic theory of gases. Air and other gases are generally good insulators in the absence of convection. Therefore, many insulating material, for example polyester, function simply by having a large number of gas-filled pockets which can prevent large-scale convection. Alternation of gas pocket and solid material causes that the heat must be transferred through many interfaces, causing rapid decrease in heat transfer coefficient. The thermal conductivity of gases is directly proportional to the density of the gas. Okay? The thermal conductivity of gases is directly proportional to the density of the gas, the mean molecular speed, and especially to the mean free path of molecule. Maybe you have a question, what is the mean free path? So the mean free path depends on the diameter of the molecule, with the larger molecules more likely to experience collision than small molecules. So imagine you have a big diameter of a larger molecule. So if has other molecule near it, so it's more likely to have the collision rather than the small one. So which is the average distance traveled by an energy carrier or molecule before experiencing a collision is called the mean free path. So it is the average distance traveled by energy carrier like a molecule before experiencing a collision. Light gases, light means it's not heavy, such as hydrogen, because only one atom. If in the gas is two atoms because H2, and helium typically have high thermal conductivity. On the contrary, the dense gases such as xenon and difluoromethane have low thermal conductivity. So this is some value of the thermal conductivity of some gases. You can see here hydrogen and helium is one of the light gas. It's higher thermal conductivity rather than, for example, krypton or xenon. Now, for the thermal conductivity of the liquid, so the thermal conduction is caused by atomic or molecular diffusion. And liquid tend to have better thermal conductivity than gases, and the ability to flow makes a liquid suitable for removing excess heat from mechanical component. The heat can be removed by channeling the liquid through a heat exchanger. So inside the heat exchanger there are a lot of pipes to remove the heat, because the liquid is flow into the heat exchanger. And then the thermal conductivity of non-metallic liquids, for example water is non-metallic liquid. The metallic liquid, for example, is mercury, because mercury at the room temperature, the phase is liquid, generally decreases with increasing of temperature. Now this is the typical thermal conductivity of water. So we can see this is the thermal conductivity, and this is not watt but milliwatt. So this is around 0.8 watt meter per meter Kelvin. And this is the temperature, and this is the saturated water. So what is the meaning of the saturated water? So the saturated water means the water almost change phase. So remember, like the saturation point at 1 atmosphere is 100 degrees C. It means at 100 degrees C, the water is between liquid or vapor or gas. So if there's more energy, so the water will become a gas. So this is called the saturated water. Means at 300 degrees C means the pressure is not atmospheric pressure, of course. We need to increase the pressure, but in this figure we cannot see the pressure point. So you need to see the steam table. So we can see that the highest point of the thermal conductivity of water is around 100 and 150 50, like 150, like in this point. So this is the 664 milliwatt per meter Kelvin. However, when the temperature is increased, the the thermal conductivity is also decreased. So it's increased at the peak point and then decrease. Now compared to the water, now this is the vapor. The vapor has the opposite value. So at the low temperature, the saturated steam or vapor, remember the saturated steam, it means it's beyond between the phase of gas and liquid. So if less energy is like the energy is given, so the steam will condensate and will be water, become water. So here we can see that with the change of the temperature, the steam will have a high thermal conductivity. So why for some industry we need called the superheated steam. And now is the thermal conductivity of a solid. So the metals, for example, the metals are solid and such they possess crystalline structure where they occupy transitionally equivalent position in the crystal lattice. Metals in general have high electrical conductivity, high thermal conductivity, and high density. And the transport of thermal energy may be due to the two effects. First is the migration of free electrons, and the second is the lattice vibrational waves or phonons. So we will not discuss about this because you need to study more about the solid state physics, so it's not our cover to this subject. And then the thermal conductivity may be expressed as K equal to Ke, it means from the free electron, and plus Kph is from the phonon. And this is the typical conductivity of metal. We can see that silver has high thermal conductivity compared to gold or aluminum. But for example, iron is not so good. Copper is also good, okay, and cheaper than silver, of course. And this is the thermal conductivity of some non-metals. For example, we can see that the diamond, diamond has the highest thermal conductivity. It means if you use diamond for the heat transfer conduction, the heat can be transferred smoothly. Okay, but the price of diamond is very expensive. Okay, that's all for today's lessons. Thank you for listening to my explanation, and remember, don't forget to do the quiz. So please see your e-learning platform and please do the quiz. Thank you and see you next week for the next lesson.